Hey everyone, welcome to Unit 5.5 video lesson. Today we are talking about feasible region. So this is going to build off of our knowledge from systems of inequalities. Okay, so when we're graphing systems of inequalities, the equations are called constraints, and they create this shaded area called the feasible region. So this is where all of your possible solutions occur in the feasible region. You can have two kinds of regions. It could be bounded, this one that you see in the bottom left, okay, where the entire shaded area is closed off by the constraints, or it could be unbounded, the one that you see in the bottom right, where one side is open and that shading will go on forever. Okay, the corners of the feasible region are called the vertices. So on this green diagram, you see all of those black points. Those are called the vertices, which are just ordered pairs. They're x, y values, and this is going to help us determine something called the minimum and the maximum values from the constraints. Okay, so we use the vertices, like I said, to produce the minimum or the maximum, and we have to evaluate them in something called the maximization function. Okay, this is also referred to as the profit equation, or sometimes even the objective function. Okay, so many corporations use this to maximize their profits. Okay, so how does the maximization function work? So it's going to use function notation, and you can see here that it's going to be a function of x and y. So that's why it says f of x and y. Okay, because we are evaluating an ordered pair which has an x coordinate and a y coordinate. And the way that we're going to evaluate that is just by substituting the x and the y values from each vertice into the maximization function. So in order to solve these feasible region problems, we're first going to graph our system of inequalities just like we've been doing. Okay, so using solid and dotted lines to graph the equations, and then using our little arrow system to determine where the shading will overlap. Okay, once we have a created graph, we can state the vertices and then plug each of those into our maximization function. Okay, the ordered pair that produces the largest value will be our maximum, and the one that produces the minimum or the smallest will be our minimum value. All right, so let's try and do one of these together. Okay, so I have 3 equations, okay, which is more than we were doing in the regular problems for 5.4b, right? And I want to make sure that everything is in slope-intercept form. So I see this first equation, I have to solve for y. Okay, but then everything else is in slope-intercept form. So now I'm going to go ahead and graph. So my first line starts at 2, and I go down 1 and to the right. Okay, and that is going to be a solid line because it is equal to. Okay, greater than is going to shade above the line. All right, my second equation, that also begins at 2, but I have a slope up 1 and to the right 2. This is also solid, okay, but it's less than, so I'm shading below. Okay, and my final constraint. Okay, and once again, greater than is above. All right, so remember, the shading overlap is going to happen where all of the arrows point towards each other. Okay, and if I actually put some more arrows on my green line. All right, so where do all of my arrows point towards each other? All right, with the addition of that new green arrow, hopefully you see that it is this triangular shape here in the middle. Okay, so this is a bounded feasible region. And I'm going to darken my vertices there. Okay, so the ordered pairs that make up my vertices, 0, 2, 2, 0, and 4, 4. Okay, so I have 3 vertices here. Okay, so step 1 is to create your graph. Step 2 is to find your vertices. And now step 3 is going to be to evaluate them in your maximization function. Okay, so your maximization function is going to be given to you. So for this problem, it's f of x and y equals 4x plus 3. So we're going to take each of these ordered pairs that are x and y values, and we're going to plug them into our function. Okay, so our first vertice produces a value of 6. Our second produces 8. And the third one is 28. Okay, so which point? Okay, and it says point, so you're giving the ordered pair. So which point is the maximum value? So which one produces the biggest value? The ordered pair of 4, 4. Okay, and it's actually blocked here, so I'm going to write above it which point yielded the minimum value. Okay, so which ordered pair gave us the smallest value? It was 0, 2. So the minimum is 0, 2, and the maximum is 4, 4. Okay, so there are not many new skills here. Okay, we know how to graph a system of inequalities. Okay, we now have to state our vertices, but that is a very simple concept. And then we're just evaluating in a function, which we know how to do. Okay, let's try one more example. All right, so now we have 4 constraints. So y is greater than or equal to 2. That is a solid horizontal line. And greater than is going to shade above. Okay, x is greater than or equal to 0. So that is a vertical line, and it's actually on the y-axis because that is the x value 0. Okay, for greater in a vertical line, We're going to shade to the right. We're going to have another vertical line on 8. But that one is less than. Right, and last but not least, I have a slope intercept. So begin at 9, and we're going down 1 and over 4. And this one is less than. Okay, so where do all of my arrows point towards each other? I hope you can see it's this 4-sided figure there in the middle. Okay, and I'm going to darken my vertices. So my vertices, 0, 2, 0, 9, 8, 2, and 8, 7. Okay, the order in which you list them does not matter. All right, so this is the first part. Create your graph and get your vertices. And now we're going to evaluate them. Okay, so plug each vertice into your maximization function. Okay. All right, so I just rewrote that because it is blocked on the bottom. So which point yielded the minimum value? Where is the smallest value? -18 is the smallest value, and that came from 0, 9. And which point yielded the maximum value? 8, 2. Okay, so remember, we give the ordered pair and not the value, because 20 doesn't tell me any information about the problem. If this had been a word problem, your variables x and y would have been assigned, okay, to actual quantities. So listing 20 doesn't tell me that there were 8 of something and 2 of another, depending on what your x and y variables are. Okay, so that is everything for 5.5 feasible region. Okay, you should have 2 completed graphs as part of your notes. And if you have any questions, please write those down as well. All right, thank you so much for watching, guys, and I will see you next time.